surveying where additive manufacturing today. And there are other people that are going to be talking about various aspects of additive manufacturing for the rest of this course. So I thought my part would be to sort of tell you a little bit about where it came from and to provide some context.
Recording has started.
So if we go to slide number 2, it should be a presentation outline. There are 3 areas I want to talk about. I split additive manufacturing history into 3 parts. There's prehistory, then there's precursor AM processes, and then what I call modern additive manufacturing. So we'll go to the next slide. The technology has, over the history of the field, which is about 30 years, has had a variety of names. Here's about a dozen different things that we've called this. Additive manufacturing only became popular about 6 years ago, but it was called by lots of names, and the popular ones are the ones that are in blue here on the right side. Specifically, the last 3. Certainly, 3D printing is extremely popular because that's been a process that the media and politicians tend to call it. Whereas the additive manufacturing has really been what the technical field refers to it as. Okay, so let's go on to the next slide. I think I covered this next one. Additive manufacturing really was adopted in 2009 by the additive manufacturing community. 3D printing has been less popular. There's reasons why we did not adopt 3D printing as the name, even though it's a really popular name and it makes really good sense. The main reason was that there was actually a process called 3D printing. So we didn't want to name the whole field after one specific process. The analogy I use is it's sort of like it's like trying to come up with a name for automobile and calling it Chevy, because it just doesn't seem to make sense to call the whole field all automobiles after one car. That's kind of what was happening with 3D printing. Is with the name 3D printing. Okay, so if we go to the next slide, this is I realize this is probably what to see, but it shows 3 different areas in additive manufacturing. If you click once, you'll see the prehistory. I believe there are 3 areas. There's topography and material deposition, and then the third area is photosculpture. We'll look at all 3 of these. So if the slide works well, you can see the word prehistory. If you click again, I think what will pop up is precursors, which are processes that were developed from about 1960 until about 1984. If you click again, hopefully eventually you'll see the Macintosh computer that pops up on the slide. What happened is that these precursor processes are people that had the right idea, but they were too early. They came before there was the distributed computing. That is, before there were desktop computers. It was the Mac in 1984 that really made desktop computers popular. IBM had sold a bunch of machines prior to that. They all operated on the DOS system, which was really fairly unintuitive for a standard user to use. Hopefully you can appreciate right now that additive manufacturing, you have to have a computer to do the process. You have to have a computer to handle the files and to control the machine, but you also have to have the computer from the user side, for the user interface with the fabricator. And if the computer is so difficult to use that an average operator can't use it, then that defeats the process. That's what happened with these precursors. Then starting in about 1985, 1996, we have the modern processes. So I'm ready to go to the next slide. I wanted to at least say something about the commercial processes that are available. This lists a bunch of the additive manufacturing processes that are commercially available. And what's notable about these, I list the date of commercialization. This is when the company was formed and actually sold the first fabricator. So stereolithography was the first one, came out in 1987. First machine sale, used deposition modeling, which is Stratasys. All the low-end 3D printers are based on this. Was laser sintering at my place. First machine sale in 92, etc. But what you have to appreciate is that all of these technologies were invented in a space of about 5 or 6 years after the Macintosh came out, from 84 to 89. And that was when the inventions took place, and then the commercialization took a few years later. My point here is that there was just an explosion of 3D printing additive manufacturing that took place in the mid to late 1980s in terms of the inventions and in terms of the development. It was all enabled by the computer, specifically an easy-to-use, intuitive computer like the Macintosh. All right, so let's look at this. The next slide shows a nice little welded cup. It looks exactly like what we see with directed energy deposition today. There's a base plate that the part's built on, just like we do today. But if you click one more time, you can see that that this actually is a drawing, a patent. It was written by a guy named Baker in 1925. This is the first of the precursor processes created in manufacturing. But again, hopefully you can see what it looks like today with an Optimex machine, which is what I show here, and with some nice parts that are on the other side that show what the modern technology looks like. But again, this traces back to 1925 at the very least. If we click onto the next slide, hopefully you see a Blanthor patent. This was a 1892, I think, patent that from Blanthor. What he did is he was doing cut and stack approach, where what he would do is he'd take blue XD and lay them over these topo maps, and then draw a line around the constant elevations to cut the sheet into two pieces. He then take those two pieces, like a positive and negative, and stack them to create a mold that, which is you see on the bottom right-hand side of this figure, that he would use then, he would finish it a little bit, then use it to print paper three-dimensional topo maps. So that's the cut and stack, or the stack and cut approach. If you click one more time, hopefully you'll see the M4 machine, which is an Irish machine. It's based on this technology. It's a nice machine because it just uses regular sheets of paper that are glued to each other, and then has a cutter that comes along and cuts it. And there's also a little printer that will jet down some ink in different colors, so you can actually make these spectacular colorized objects. The little shrunken head here that you see is one of the principles of the company. It's about 3 inches tall. That was made using this technique. If you look very carefully, you may be able to see a layer line, but they're very, very difficult to spot. So anyway, so this is, again, our modern technologies that come from prehistorical development. So we have material deposition, and then topography is the second. The third one is photosculpture, which is the next slide. This shows a couple of photographs from Francois Willebé's photosculpting studio in 1862, the 1860s. He was in Paris, and what he did is if you look on the right side, you see a subject. This is Admiral Farragut, who was a Civil War hero from the United States. He's sitting on this platform that's split into 24 different sections. And if you look at the black boxes behind the figure on the wall, those are actually behind those windows are cameras. There were 24 cameras around the room, and Willebé would shoot simultaneously photographs of the subject at 360 degrees. And then what he would do is he'd take silhouettes from those photographs, and using the contraption that's to the right of the image on the left side of the photograph, the thing that looks like a linkage contraption, he would use that to create a 1/24th wedge of the sculpture, which he would then have an artist assemble to create the finished object. So he's using photography to create these sculptures. If you click one more time, hopefully what will pop up is a photograph of a former student of mine. This is Farshad Khan, an undergraduate, who used this a modern approach to photo sculpture. He used this free software download called Catch 1, 2, 3 from Autodesk. It's a cell phone application, so you can download it to your cell phone. And the way it works is you have a subject stand still. You open the application and you get the camera feature on the iPhone. Then you march around the subject, you take random photographs of the subject. You have to do like 30 or 40 photographs. And these upload on the cloud to the Catch 1, 2, 3D software. And then what the software will do is it will stitch those together using image recognition software for photographs and create a three-dimensional object, sculpture as it were, as a point cloud, which can be converted to an STL file, which can be downloaded and then printed. So what he's holding here is actually a print of himself made on a 3D printer using Catch 123D, this photographic software. Okay, let's look at some of the precursor processes. The earliest one is this one by Swanson, 1968. He shows basically a 3D copier in his patent. On the left side, he has laser interferometers to capture the geometry, the geographic image of a part, like this cone in this case. That worked really well. But then he would shoot it over to the printer, which he had 2 crossed lasers, and the plan was that where the lasers crossed, the energy would be different, and we could actually create the object in space. This was never reduced to practice. People have tried to do this. It simply can't be done. The closest that we can get is 2-photon polymerization, which is used to make really small objects, where in this case we can create an object in volume within a stereolithography fluid. But to make a regular object, this just simply doesn't work. So, but this was the earliest one I've been able to find. If you go on to the next one, should be Seurat's powder laser process. Seurat was a Frenchman. This was a German patent application in 1972. Was never actually issued, but he did do the application. But if you look at this, this has all the features of directed energy deposition. Or like the Optimec process, you have powder in a feeder that comes down, sprays it through 2 energy sources, could be laser or an electron beam. That's a 7 and 7A. Then the parts being built that you see there, and then the powder's cycled back up to the popper. So this has all the features of modern Optimec lens type technology, or PALM or LAMP. There are a number of companies using this, but it was done here in 1972. And the reason that Seurat didn't make a mint off of it is because there were no computers to drive this, so there was no way to get the geometry information input. There was no way to talk to a user to make it happen. Okay, charging ahead, the next one is Householder. This shows 2 systems by Householder. The one on the left is the one that's important. Basically, in 1979, he invented laser sintering. This was 8 years before Carl Deckard at our place in Texas invented it. And what he's got, if you look at the left side, going from the top down, he's got all the features of modern stereolithography. He's got the laser at the top. He's got the 2 scanning mirrors. Going down, he has the laser rastering over a surface. If you look at the platform or the powder bed, he even has a recoder blade, just like what we see in the EOS machines today, running back and forth, spreading powder. Again, this was done in 1979. Didn't go anywhere. It's because there were no computers to drive it. The next one is Kodama. He was Japanese at a research institute. He invented stereolithography 3 years before Chuck Hull did. And what's shown here are 3 images for producing the part. He has in A, the top-down version, which is what we use for mask, which is what's used today with the digital micromirror arrays. In number B, he has the bottom-up printing, which if anybody's familiar with Carbon 3D's clip machine, where they build the object out of the liquid, that's exactly what this is. Again, done 25 years before Carbon 3D did it. And then in C, it shows a gantry with a moving light source, which again is a common method for doing stereolithography today. So again, this was 1981. Going on to the next one is Herbert. He was at 3M. In 1982, he also invented stereolithography. He's got the laser, he's got the photopolymer, he's got the lens for moving things around. He's got a plotter that actually will move the beam around. It was an HP 7225A plotter to move the part around. So he also had invented stereolithography before Chuck Hull did. Chuck Hull was the founder of 3D Systems. So this shows the same deal. And again, the deal is that there was just no way to have a computer interface for people, for the operator, for the part generation, and to talk to the machine. It was just too difficult to do back in those days. Okay, so if you jump ahead, this is one of my favorite slides. It's first articles. This shows the first articles that were produced. It shows Kodama stereolithography, Herbert stereolithography, Carl Deckard at my place built his first part produced in using laser sintering. And then there's Householder's sand castle pyramid that he built using laser sintering, again, back in the early or late 1970s. We've certainly come a long way since this. Okay, so anyway, moving on through the history, it was in 1986 that Chuck Cole and Raymond Freed formed 3D Systems. 3D Systems is a very, very big company, still in business, going strong. One of the two big additive manufacturing companies in the U.S. and the world. And it was the first. The SLA-1 was the first commercially available modern additive manufacturing system in the world. Appeared in 1987, so it's been almost 30 years ago that additive manufacturing started. So it's really popular today. It's all a buzz, but the process actually, I say the beginning of additive manufacturing was 1987 with the sale of the SLA-1. Okay, just have a few more slides left here. I did want to say one thing about the future of additive manufacturing. I used this slide to do it. This is from a study on additive manufacturing that was done in 1998. Back in those days, this technology was called rapid prototyping. So you see rapid prototyping here, and what they show is that there really are, it shows a bifurcation of processes. They said that in the future, there were going to be these so-called design verification systems moving forward from 1998, where a design verification system, this actually panned out, this really occurred. These are what today we call all the low-end 3D printers, the MakerBots and the RepRats and the Fab@Homes. Those are all these so-called design verification systems. But then they also said that there were going to be these direct manufacturing systems, which has actually panned out as well. These are high-cost machines that produce parts that have engineering quality for use in service applications. And while some of the details on this slide, in terms of what could be done with these machines, is incorrect, certainly it's true that we have these really expensive machines and we have really cheap machines, and both of them are going strong today. The reason I mention this in terms of the future is I believe that over the course of the next 5 to 10 years, these two are going to start to converge back towards each other. So the two curves are going to come back together. Whether they actually come together or not is a matter of speculation, but I think the trend is going to reverse. And the reason why is because I think that these expensive printers are going to come down in cost because the patents are all expiring, and there's going to be increased competition. And more people are going to enter the market, and that's going to have an impact on the cost of the fabricators. Which is going to have an impact on the cost of parts produced. So the part cost is going to come down. That's going to turn into a vicious cycle, which is going to make the machines more desirable, and so the cost will continue to come down. Feedstock costs will come down as well. On the 3D printer side, on the cheap low end side, what I see is going to happen is that there's a lot of people getting into the game in terms of research. There's a demand for higher quality parts coming out of the low-cost printers. And so I think the quality of the parts produced out of the low-cost printers over time is going to improve perhaps substantially, perhaps even to compete with the high-end printers. And that's going to cause the verification system to move back up. So anyway, so that's my quick run on at least one aspect of what's going to happen in the future. Finally, I guess for my next to last slide, I have the conclusions. Additive manufacturing, I think it has a rich past dating back over 150 years. For precursors, I think that the technology is going to continue to grow. I'm sure Terry Wohlers last week talked about that, what the growth of the industry is in terms of the next 5 to 10 years. I think market penetration is going to increase because people are going to find more and more uses for these technologies and for parts produced from them. I think we're going to see a proliferation of fabricators, primarily driven not only by just interest in the field, but also by the expiration of patents. I would mention, by the way, the explosion of the material extrusion machines, the MakerBots and the RepRaps and all those low-end printers really occurred after the Stratasys original patents expired that issued back in the early 1990s. And then finally, I think the future is exciting. I think we have there's a long ways to go. I think we haven't seen the best of what additive has to offer yet. And so that makes it really exciting for everybody. And with that, I get to the last slide, which is shows simply a view of the campus of the University of Texas and sort of a little trigger point where we are on the map of the United States. And thank you for letting me. Okay, I'm back.
I'm back.
Thanks. Oh, thanks, everybody.